yesterday I introduced you to the beauties of constrained Hamiltonian systems, and we'll pick up right from there. Let me just write down kind of the important relations that characterize those, which we got to know yesterday. Yes, good try, Andrzej. Those two. Okay, now. So we are looking at first-class constrained systems. And of course, it won't surprise you in the course of the morning that general relativity will, of course, turn out to be a particular case of this. Now, how were those systems given to us? As a bunch of constraints on phase space variables Q and P, A running from 1 to M. Now we're in the finite dimensional case still. And Poisson brackets of these constraints should vanish on the constrained surface. And it turns out that the vanishing, in finite dimensions, the vanishing just implies that the right-hand side must necessarily be a linear combination of the constraints themselves. That's no longer true in infinite dimensions, actually. And the other condition involved the Hamiltonian. So we're interested, of course, in dynamics, not just kinematics of some phase space variables, but the Hamiltonian, in order for there to be a consistent time evolution, this had to be also satisfied. And we saw kind of a twofold interpretation of that at the end of yesterday's lecture. So, and to remind you, these wiggly equality signs go by the name of weak inequality and mean equality on the constrained surface defined by the simultaneous vanishing of these M first-class constraints. Now you could say, everything weakly commutes on the constrained surface. I mean, the Hamiltonian and these constraints. So that's maybe to remember this. So the interpretation of this here was that the Hamiltonian, if I now look at the flow induced by the Hamiltonian, it will, if it starts on the constrained surface, it will remain in the constrained surface. So the integral lines of H stay totally within that surface. And at the same time, in order to make, well, not in order, but that's one consequence. Another consequence of this being satisfied is that the Hamiltonian evolution is unique, because the other directions, I mean, we saw yesterday that potentially, the time evolution might not be unique, but by requiring this, it just declares that these other directions are gauge directions, in which the physics doesn't change. Now, I also drew a little picture yesterday, and I'll repeat this today, and that illustrates the following fact. This is how it's sometimes phrased. If you have a first-class constraint, it strikes twice. This means it removes effectively 2 dimensions from your phase space. The first one through the reduction to the surface, and the second one through defining an equivalence along, a gauge orbit on that same constrained surface, which in principle I want to get rid of. It's not relevant for physics as such. So that's captured by saying that they strike twice and relates to the degree of freedom counting. So firstly, as I already also mentioned yesterday, they constrain us, the dynamics, to a subspace as constrained subspace of the phase space of dimension 2n minus m. And secondly, they induce a foliation on that constrained surface. They induce a foliation of SC into gauge orbits. Gauge orbits. So each of these gauge orbits has dimension m. And the fact that this is true rests also on the assumption that I've stated somewhere along the way, that these are really independent, they span independent directions in phase space. Okay, these m constraints. So what are the gauge orbits? How can I get them? Well, I just get them by kind of integrating up the flow along the Hamiltonian vector fields corresponding to these m constraint functions. So this is generated. One also says the symplectic flow. That just means one walks along the directions of these Hamiltonian vector fields, which are called capital X, associated with this bunch of constraints. And the picture we drew was right as follows. This was my phase space. Here was my constrained surface defined by the joint vanishing of all the phi i's, phi a's. And on this, in every point here, of course, there are various directions spanned just by the flow of these X Hamiltonian vector fields associated with these phase space functions here. And if I start integrating those up, I get the gauge orbits, each of them of dimension m, right? And then I get a foliation of my phase space. So points along one and the same gauge orbit are physically equivalent. And my physical phase space is given, I can write it like this, as physical is equal to points of the constrained surface with the equivalence relation of lying on the same gauge orbit. So and this has dimension as phys, has dimension 2n minus 2m. So it's a space of gauge orbits. And well, a lot of difficulties are associated with the fact that, well, that is not necessarily or rarely a linear space, and therefore you have kind of typically trouble finding global coordinates of this. So this is not necessarily a space that is easy to describe in practice with the explicitness that is often needed for making concrete physical calculations. Now, second-class constraint systems, we're not going to talk about, but for those, the degree of freedom counting is different. For those, you only subtract 1 degree of freedom per constraint. These second-class constraints only appear in pairs, and what, roughly speaking, characterizes them is that if I kind of look at the matrix of these objects, it will have a rank on the constraint surface that is larger than 0. Okay, and that's of course only, well, so they have to, for example, if I have a pair P1 and Q1, and these are two constraints, they form a pair of second-class constraints. Of course, they don't commute with each other, you see. So they're not, they don't satisfy this relation here, but they're just proportional to their Poisson brackets are proportional to the identity, right? And so you can think of them as kind of removing second-class constraints as kind of canonically conjugate pairs. Yes?
So the first-class constraint, does the physical space actually have curvature? Because what is the obstruction that's causing us not to be able to find?
Well, what curvature is, of course, an additional geometric structure. Well, it often has, it's often not a linear space to start with. Okay. So then already you know that you don't have kind of a single coordinate system typically that will cover all of space. So it could be something relatively simple. It could be something like an affine space, but usually it's something more complicated. And it might even have a rather non-trivial topology. I mean, because topology, in the sense of infinite dimensional configuration of phase spaces. So things can certainly get rather nasty. And in 4 dimensions, if you look at what the physical phase space is for gravity, it's something that's only rather partially understood. I mean, this quotient in terms of its explicit kind of geometric properties. Now, one important ingredient that comes up in this kind of in this type of first-class constraint systems we haven't, well, not discussed, or well, implicitly we have already discussed, I should say, by saying something about the Hamiltonian here, is the following. Now, I have such a first-class constraint systems. I have kind of an action of if it can be integrated, perhaps a group of symmetries, certainly on the constraint surface. Now, what are the observables, even classically, of that theory? These are the phase space functions that are themselves independent of where I am on a gauge orbit. In other words, they are things that are constant along gauge orbits. Only these are well defined on this quotient space, this physical phase space. And of course, it's straightforward to write down what the condition classically is for an observable. It's the same we required up there for the Hamiltonian. So physical observables classically are phase space functions, capital F, Qp, which satisfying that their Poisson brackets with all the phi a's are weakly 0 for all a. Yes, and again, I can read this as if I follow the flow lines, of the Hamiltonian vector fields associated with these phi's, this F will stay constant. And therefore, so that's the same as saying F is constant along the gauge orbit. And of course, in that case, F will project to a well-defined function on this quotient space. On S. So the Hamiltonian will certainly be always one of those, but of course there are more. I'm interested often in a larger set of observables to describe the physical properties of my constrained system. Now, what are a number of good references for this? There is a classic reference by Paul Dirac, contained in his lectures on quantum mechanics from 1964. And it just stands out in the clarity of the argument of discussing, the various things that can happen in finite dimensions. So that's certainly very helpful. There is a great book for the practicing physicist by someone called Kurt Sundermeier. That's out of print. That is a rather old book published by in the Springer lecture notes series. It's called Constraint Dynamics. I think it's out of print, but you might be able to find a copy if you're lucky. So what makes this book so nice is he puts all the, he has a general mathematical and geometrical discussion, but then he goes through a whole bunch of physical systems in finite and infinite dimensions completely explicitly. And it's a reference that I just found so helpful as a student. So it's not just formalism, but things are discussed and difficulties are discussed. And gravity is also discussed completely explicitly, the constrained formalism for that. That's something we'll learn about later today. And of course, by now it has found its way into various other textbooks. I'm just mentioning one by Inno and Teitelbaum, Quantization of Gauge Systems. Quantization of Gauge Systems. It's from 1994. So also to emphasize, this is really standard material, and it pops up, everywhere. So it's certainly not a waste of time to learn about this. Now, interestingly, what triggered much of the early interest in these constraint systems was exactly trying to understand gravity and understanding that, even classically, the dynamical degrees of freedom of gravity. And then this whole formalism was developed. It's often associated with the name of Dirac and also Bergmann or Bergmann, Peter Bergmann, who were some of the early pioneers in thinking about gravity. It's also called, so what I've shown you a little part of, is also what sometimes goes under the name of the Dirac Bergmann algorithm. So that just means, I give you general Lagrangian, and you run through a procedure of systematically identifying constraints, first or second class. There are also other distinctions one makes. And in the end, you know what the physical degrees of freedom of your theory are, because if just someone presents you with an arbitrary Lagrangian, it's very difficult to see sometimes. Well, what is its physical contents? Certainly, also classically. Okay, now, this brings us now straight to the discussion of the theory we are really interested in, which is, of course, general relativity. So what's the canonical formulation of GR in the context we've just learned about, that of constrained dynamical systems, albeit in infinite dimensions now for, of course, a field theory. And this discussion is very crucial to enable you to understand of why one wants to do certain things when one canonically quantizes this theory. So that's really a necessary prerequisite for you to understand. The very simple examples we played with until now were always from, non-relativistic mechanics. And well, one particular feature is, of course, that they have a well-defined, you know always what time and space are. This is just Newtonian. Right? Of course, in particular, you know what time is. And it enters crucially, if you think about it, in the way we set up the Hamiltonian formalism, because to define the conjugate momenta p in the first place, you look at the Lagrangian, and you take the partial derivative with respect to the velocities. Now, when you're talking about velocities, of course, you already know what you mean by time, right? So a notion of time goes into the description at the very first step, you could say. Now, gravity is a theory which has a large invariance that under general coordinate transformations, and in particular, there is a priori no one notion of time that is singled out. Now you ask yourself, now, how will this be reflected in a Hamiltonian formalism? This arbitrariness of being able to choose a time. And it will turn out this will exactly be encoded in an algebra of first-class constraints, which will be just characteristic for that theory. And because it's kind of, it contains a lot of information about what this theory really is about already classically, it's certainly one of the structures that one might think of translating into the quantum theory. And the difficulties that ensue when you try to do that, well, we'll get to, not today, but from tomorrow on. Now, what are my ingredients to start with? I am given some manifold, topological differentiable manifold, usually, with additional data, which is a Lorentzian metric, right? Just a 4x4 a tensor. And what, moreover, one specifies usually classically is that this M has a product structure. So there is something like a time direction, and what happens in the spatial slice is, well, it's more or less arbitrary. So an assumption that one almost always makes in the classical theory is that M4 is actually given by, topologically, by a Cartesian product of the real axis. Think of that as the time direction, times some three-dimensional manifold, which will, well, this will become, of course, kind of space, so space and time. At this stage, of course, I haven't even talked about a metric, but this is, of course, where coordinates will make an appearance. Having given these data, one goes one step further and introduces a notion of time that is global. And kind of it fits with this choice in the sense that M, with this choice of time, is foliated into Cauchy hypersurfaces. And, well, these are spatial. So this, the induced metric on these hypersurfaces is spatial, induced from this G mu nu here. Hypersurface just means codimension 1. So in 4 dimensions, these are the 3-dimensional surfaces. Cauchy means, I can give initial data on them, for which then the time evolution will be uniquely determined, hopefully for a long time. So that's one starting point. So you might say, okay, what is this time? Well, at this stage, that is in nowhere you should think of that as a physically distinguished time. It's just a parameter. I mean, I have to start I'm in the continuum, so I have to start describing what my degrees of freedom are. Right? So, and I just, using this product structure, I can always find such times. But the choice per se is arbitrary. So let me make another little picture. This stage. Why did I get this? Okay. Now here's my manifold M. This piece of blackboard. Now, let time go up in my picture, and let there be such a foliation into surfaces kind of sigma at a given time t. So there's one for every moment, but I just draw a few. So this is my sigma at time t, sigma at time t prime, sigma at time t double prime. And so as I said, I mean, t at this stage has no distinguished physical meaning. It's not implied by this construction. Well, it's a time variable, all right, which means that one thing, I mean, I'll immediately be introducing is kind of a normal everywhere on each one of these spatial hypersurfaces. A normal, of course, normal with respect to this four-dimensional Lorentzian metric. Of course, this is now a time-like vector. So a time-like vector of unit norm, because it's time-like, and my metric has signature minus plus plus plus. Its norm must be -1. That is, by construction, just perpendicular on all these slices everywhere. So here is my normal vector, little n, I call it, is the unit normal vector on all the sigma t's. So it squares n mu downstairs, n mu upstairs, equal to -1. Of course, this index I have pulled up with a metric g mu nu. And therefore, well, I can now write down what my induced positive definite 3 metric is on every slice. On each sigma t is h mu nu, so little h, equal to g mu nu plus, so a term now bilinear in this normal. And of course, what you can immediately deduce, why is it spatial? Well, if I dot it, if I take the scalar product, contract index mu with h mu nu, you immediately see that this vanishes, right? N mu times a g mu nu just gives an n, this same little n, with an index nu downstairs. And of course, multiplying it into here, I just get the n mu squared, which is -1, and the n mu downstairs. So this is 0. Now, I hope that has come up already in Ruth Gregory's lectures. This is also called the first fundamental form, I mean, pertaining to this codimension 1 slices. That's the induced metric. So what we're doing here is we are rewriting, you could say, the g mu nu, the space-time metric, as spatial metric plus now additional data, and we're now going to rephrase what we mean by how we parameterize the additional data that are needed. So there are the 0, 0 entry of the Lorentz metric and the 0i and I0 entries of that metric. Yes, and here it's helpful to make another little illustration. Now let me pick out a couple of slices. So where I'm now imagining that, so these are two infinitesimally close spatial slices sigma. So let this be here sigma t, and let this be sigma t plus dt, a small unit of this arbitrary time I've chosen. Now I'm interested in kind of splitting up space-time distances into a space part and a time part, as kind of is already being suggested. Well, you know, I want to work my way towards a Hamiltonian formalism. So there is a time, and I want to be able to define momenta. Now, the way to do it is the following. So just imagine just some point down here. It's coordinates x, I, and t. So I just have made some choice of coordinates in an infinitesimal neighborhood. Now, up here, I pick an arbitrary point that is infinitesimally away from this thing here below. xi plus dxi. Okay, point be here. And it has coordinates t plus dt. Oh, just for clarity, let me put it over here. Now, these are 2 points. And there will now be a invariantly defined 4 distance separating them, a proper distance. Right? Let me call this ds. I now want to rewrite it in terms of quantities that are specific to this slicing. So one way of doing it is the following. Now, starting from this point here, there is a distinguished direction. It's a direction of the perpendicular vector of this normal vector, little n. Okay? So, and what I certainly can do is I can erect here. I can walk up in that perpendicular direction until I hit this surface. So this is infinitesimally close, and it gets me to some point here, say. So let me draw, well, a right angle in Lorentzian sense. Yes, it's clear what this means. So this is the direction of the normal. Now, this will be some distance away. The point I meet, well, so this point will have some coordinates. And the coordinates I decide to call xi minus ni of x dt. And of course, the time coordinate, well, it's still the same because I'm on the slice that is a dt away from the lower slice. So the time coordinate is still t plus dt. So this introduces what I call a certain shift, and we get to the interpretation of that in a second. Now, the length here of this, right, is some multiple of dt. And this multiple I'm calling capital N. Now, n times dt is, by definition, the geodesic distance between this and that point. So that, again, not a coordinate quantity, but a physical quantity. So in that sense, the n gives me the proportionality factor of my arbitrarily chosen coordinate time with what is kind of true proper time. That would be the time experienced, say, by an observer that starts falling freely in that direction. What she would measure on her clock. That is kind of detour, if you like. Okay. Now what I'm going to do is I'm going to write down Pythagoras' theorem in Lorentzian metric to express this distance as a function of this distance here and that distance up there. Okay, so this is kind of my triangle, if you like. And there's a right angle up here. Right. Now, what is the suitable form? So what is the Lorentzian version of Pythagoras' theorem? It is ds squared, so that's kind of the long side here, is equal to minus. Now, let me first write it in words. So, proper time elapsed from sigma t to sigma of t plus dt, all squared, plus kind of proper distance in the three geometry, all squared. And the minus sign comes, of course, about because of the overall signature of my metric. It's not Riemannian, but pseudo-Riemannian. So what is this? Well, the proper time here is just this n times dt, as I just explained to you. So that's detour, if you like. So it's n of x times dt squared. Now, what is the proper distance here? Well, that's easy. So I just take the difference of the coordinates here. And you see, of course, it has the same t coordinate. I have to compute, this minus that. The xi will drop out. What will remain is the dex d xi times, plus ni dt. This is kind of the coordinate distance. Now, to get the true distance, I have to multiply that into the three metric on the surface, which was this hij. So what this is an hij. That's, of course, spatial, as you've just learned. And now, ni dt, that's a kind of infinitesimal coordinate distance, which I have to square. Well, and square means, of course, I contract it with this two-tensor, spatial two-tensor, plus nj dt. So this here, well, I should also write, sorry, just for generality, because I've included the argument here. Of course, that depends on where I am in general, this ni. So this is a three-dimensional vector, and that's a number in every point. This is called the lapse function. Lapse function. Because it tells you how much proper time has elapsed when you walk a coordinate distance dt. This thing here is called the shift vector. Now, what is the meaning of the shift vector? The shift vector tells you how much the coordinate that sits here kind of orthogonally or directly above my xi point, how much that coordinate has shifted in the spatial direction. So the special situation that the shift is 0 would correspond to a situation where, when I go up here, kind of perpendicular, I meet the point that has exactly the same coordinate xi. So this tells me something about, well, how I've chosen my coordinates in the first place. So if that was the case, then the shift was 0, but that doesn't necessarily have to be the case. And then you get a non-zero shift vector. Now, the whole point of this exercise is that you have now expressed what was the 4-dimensional Lorentzian metric G mu nu. You have now split it into information that was the spatial metric, so induced on these hypersurfaces. I mean, that was clear. But I said, of course, there's more information in this. And this has now been encoded in these 4 functions, namely the lapse and the 3 components of the shift vector. So this is the additional data I need for the information to be preserved, you might say. So this is, of course, a symmetric 4x4 matrix. It has 10 entries, independent entries. This is a symmetric 3x3 matrix that has 6 entries plus 4 is 10. So 10 degrees of freedom. I have now rewritten in a form that's adapted to this slicing. And that will enable me to set up a Hamiltonian formulation. So these were 10, 6, plus 1, plus 3. And I can simply now write my whole matrix this way, if I want. I can just read it off from here. I have a time coordinate. I have here spatial coordinates xi. And I can now read off what the metric becomes in terms of these new quantities. So this is G mu nu, my original. So that was G00, G0, J, Gi0, Gij. Now, if I rewrite it in terms of these new coordinates on configuration space of my gravitational theory, it becomes the following: nk, so the shift vector squared, where by definition I'm pulling indices up and down now in these expressions with the 3 metric Hij, because I'm no longer in this situation where I'm working with the G's, but only where I'm working with the H's. Right? Minus n squared. Then here I have an nj, here I have an ni, and here this lower 3x3 block is given by the Hij's. And this you just read off, the coefficients of the dt squared, the mixed terms dt dxi, and the dxi dxj for this line element. And then it's straightforward to compute also the inverse. I'm not going to do this here on the blackboard. You see, now we've also rephrased. We are on our way to getting where we want to go. Now, what will become of kind of a space-time configuration G mu nu is something I'm thinking of as a time evolution of this Hij's, this first fundamental form. Right? And, well, the shift and the lapse, they will give me additional information that will just say, well, how is the parameterization on these slices? How is it related? And that, of course, will depend on specific coordinate choices. And this will essentially turn out to be kind of freedoms of the theory, which I can just choose arbitrarily without affecting the real physics, the real geometry. Now, so these here are my candidates for coordinates on phase space. Now we need canonically conjugate momenta. So we have now a T, although it doesn't, I said it doesn't have any a distinguished physical meaning. But what are now the momenta? So what are the field velocities to start with? So now think, well, this is still what I wanted to write down. So this M G mu picture we started off with now has been rephrased in a way that will enable us, or that make it natural, that's what we're after, of course, to think of that as an evolution of data given on spatial hypersurfaces, namely of the remaining HIJs. Of course, they depend also on X, but I'm emphasizing here the T dependence. So these are my kind of field coordinates, you could say. They are natural kind of velocity variables. And the answer is yes, they are. And the answer should already be familiar to you from your course in relativity, I hope. So what are natural notions of a velocity? There's a component of the so-called intrinsic curvature, for which one uses the symbol capital K, usually. The 2 tensor. And I get it by, in terms of the quantities, 4-dimensional quantities in this fashion. So this is the H mu nu that appeared here. So this still has all the 4-dimensional indices. The covariant derivative is still that of the 4-dimensional metric G mu nu. And this was just my normal vector. So this here is now given in terms of 4-dimensional data, you could say. Now, what may I remind you of the geometric meaning of this expression? Okay, I hope this is still visible. So I'm now imagining, right, I have now spatial slices defined. And what the extrinsic curvature gives me is, well, as the name says, it's not a measure of how this 3-dimensional surface is intrinsically curved, but how it is curved when viewed from the space, the 4-dimensional space it is a part of. Yeah, so that's, of course, it's just geometrically a different thing. Now, how can I understand the geometric meaning of this expression? Well, anywhere here now, I have my normal vector. Maybe I should draw this picture a little more extreme, a little more curved, then things will become slightly more obvious. Let it be like this here. Now, when I'm here, of course, the normal vector will point this way. So what means kind of big extrinsic curvature means kind of parallel transporting this guy to here and seeing that it has made a big jump means, well, this was extrinsically curved because here it just goes down in the dip. Yeah. So if I parallel transported this here, it would end up here, and then I would compare it with the normal at that point, and I see a big difference. Now, the covariant derivative is exactly comparing these two vectors. What this is a projection of this quantity onto the slice, the 3-dimensional slice. Yes? So I'm now projecting, if you like, this difference vector. I'm projecting it down to here. And that's the meaning of the extrinsic curvature. So it's rather transparent from this 4-dimensional picture. So this is x plus dx Oops. So this is my parallel transported vector. Transported normal, and you compare it to the normal at that point. So this was my little n at x, and here was my n at x plus dx. Okay. Now, from this construction, well, it's fairly obvious that this is actually a spatial quantity because I'm just projecting it down. So, so that there are two fundamental properties this extrinsic curvature has, which one can work out, are not immediately trivial to read off from this expression. So first is that it's symmetric in these two lower indices, and then also that it's purely spatial. So if I contract it with my normal vector, the result is 0. So this is a so-called intrinsic curvature. And it's also called the second fundamental form, if you've come across this expression already. Now, explicitly in terms of the new data here, let me just write it here because there's no space down here. Kij, this is all I have to give you, I told you, is 1 divided by 2 times the lapse, h dot ij minus spatial covariant derivative of the lapse in the symmetrized fashion, dij minus dj and I, where these are now spatial covariant derivatives. So in contrast with this object, which was a space-time covariant derivative. Yeah, so this was the statement is now that this is a natural kind of velocity variable, right? So, which you see from here. So it has, the hi dot, but it's natural to keep these shift components with that here.
Covariant derivatives.
Yes.
Are they the components of the four-dimensional?
No.
They're not.
No. I think it's, well, you can work it out. It's slightly more complicated because I have this projection there. No. But of course, if you keep track of the fact what is and is not orthogonal in this picture, you'll be able to work it out geometrically. Or otherwise, well, you just follow the algebra here. Now, so steps should be clear. What I do is I take my gravitational Lagrangian. Now it's expressed, first of all, it's not yet expressed to me in the standard way as a function of coordinates and velocities, but that's the first step I make. And then canonical conjugate momenta will be introduced, and they will be given by partial derivatives of your Lagrangian with respect to hij dot, n dot, and ni dot. Okay, the velocities of these new variables here. Yes?
When you write the metric in terms of n's, and is it obvious that you maintain the same signature?
Well, yes, it is. Well, it is, of course. Well, this is, a non. Of course, you have to show that it's a non-singular transformation in the first place. And if you make that sure that this is the case, then of course you know that nothing can happen with the signature. But of course, you might also say, well, it's obvious by the geometric construction I adopted here. Of course, I'm just defining the n's as specific, geometrically motivated functions of these G menus. So yes, indeed. I mean, so what you can see here, for example, one thing that is always true is that this n here will be positive. So if it vanished, well, then you'd have a problem with your metric, because then the time direction is just not, for instance, well defined in a point. So there are also, just to say, there are also some restrictions that reflect the old, for instance, the fact that the signature of G mu nu was the same everywhere, and that the determinant couldn't vanish. Of course, that translates now into certain conditions on the n's and the ni's and the hij's. But yeah, otherwise it's just locally, certainly a map that always exists. And I can always describe things locally in terms of these so-called ADM variables. That's also what they're sometimes called. Okay, now. Now, what was my Lagrangian density for gravity? Okay, let me include kind of the overall coupling constants. Let me write it as 1 over kappa squared. So kappa squared is 16 pi g Newton. And other than that, the Einstein-Hilbert Lagrangian is just a minus determinant of G. So that's still my full 4-dimensional metric, times, now, the Ricci scalar. So let me drop, for the time being, any cosmological constant term and just concentrate on the curvature, the standard curvature term. So now, just to be careful with what are 4-dimensional, what are 3-dimensional quantities, I'm using the superscript here. So that's a 4-dimensional Ricci scalar. Now, this still is not written in a very explicit way as a function of these velocities, but this can be done. And, well, this means I have to make partial integrations in order to get there. So the modulo a total divergence, I can rewrite things in such a way that they do depend on these variables. Now, so the first thing is kind of relatively straightforward to understand. So what becomes of the square root of this 4-dimensional determinant is kind of n as a determinant of the spatial metric. Now, the 4-dimensional Ricci scalar can be split up into the 3-dimensional one, plus terms depending on my velocities, the extrinsic curvatures, minus capital K squared, where K, by definition, is, well, the trace of K. So I write it with one index up and one index downstairs, or I contract it with a metric just in this manner. Now, the first thing to notice is, keeping in mind kind of this definition I've given you for Kij, in terms of time derivatives, the only time derivatives that appear are the time derivatives of little hij. So neither this lapse function nor the shift function appears with time derivatives in this expression. And of course, that already gives you an idea that they are not true dynamical variables, right? Otherwise, they would come with a standard, whatever, n dot squared term in the action. This is not the case. And of course, it will turn out there will be a very good reason for why this is not so. Now, let us compute momenta. Capital P mu will be defined as the momenta associated with the lapse and shift, where I'm now adopting kind of a I'm putting them together into a 4-vector. N mu, by definition, is N, Ni, just for compactness of notation. Now, so these are the canonical conjugate momenta, the P mu, sorry, here. I want to write it, but of course I've just told you, you just see for yourself that it doesn't depend on these time derivatives. So these vanish. So already we've picked up 4 constraints, okay, on my phase space. The other things, so the other conjugate variables are called little pi, ij, and they, by definition, are the partial derivatives with respect to the velocities of hij. And, well, that's a simple algebraic step. I just write down the result for you. 1 divided by kappa squared, square root of h. So if I just write an h here, it just means a determinant, under the square root, k ij minus k hij with indices upstairs. So there's absolutely nothing deep in here. I'm just now following my usual algorithm of getting to the Hamiltonian formulation. I mean, I'm implementing a Legendre transformation. But of course, I can already see that I'm picking up constraints here. Now, I have the following non-vanishing Poisson brackets on the space of my, on this phase space of my field theory, classical field theory. So now, of course, since I'm talking about fields, I now will have to specify that I'm talking about eco-time Poisson brackets. And these are as follows. N mu x with p, capital P nu of y, Poisson brackets taking at equal times, x0 equal to y0, is just equal, to delta function on the right-hand side. One delta function with respect to the tangent space index, mu, and a 3-dimensional delta function with respect to the spatial arguments, x and y. And similarly for hij and the conjugates pi kl, also at equal time. Now, the only slightly non-trivial thing is these are both symmetric tensors. So that's then reflected in a specific structure for the delta functions that appear on the right-hand side, which must share the same symmetry properties. So here the right-hand side is 1/2, let's put this up a bit, 1/2 delta I k delta jl plus delta I l delta j k times the 3-dimensional delta function of x vector, y vector. And finally, I should write maybe here. Now, what is the action in canonical form as a function of these? In canonical form, using already my Q's and P's here, it's the following. It depends on hij, pi ij, n, and n I. Now, I make now a 3+1 split, integration dt, and I split off from this an integration over my sigmas, d3x, pi I j h I j dot. So that's my standard p q dot term minus Labs function times a function which I call curly h, perp, minus shift vector times some other phase-space function hi perp, where now I have to write those down for you. That will be my last deed of the day, or of the lecture rather. So the Hamiltonian, therefore, is this piece, right? I'm just taking the Lagrangian, rewrite it as PQ dot minus stuff, where stuff is Hamiltonian. So I can read off that Hamiltonian, H, let me write the dependence on these n's and ni's here explicitly, is kind of for fixed time, a three-dimensional integral n h perp plus ni curly hi. And here I'm giving you what these functions are. Now finally, curly hi of x, h, and pi. So I'm adopting this notation to say, of course, it depends on fields. Implicitly and explicitly, so is a space, has still a space time dependence, and depends on h and pi, and it is given by minus 2 del j spatial covariant derivative pi I j of x. And what is this h perp? That's slightly more complicated. H perp is of x, h, and pi is, by definition, a k squared, kappa squared, g, this I define also for you in a second, ij kl, that also depends on, well, x and h, as it turns out, pi ij, pi kl, minus square root determinant spatial metric divided by kappa squared times the three-dimensional Ricci scalar. Okay. Where this g, I, j, k, l is the following function of the three metric 2 square root of h, h, I, k, h, j, l, plus h, j, k, h, I, l, minus h, I, j, h, k, l. So just listen to me for one more minute while Ruth is standing threateningly at the door here. Now, what is this? In part, this is not unexpected. What should a Hamiltonian be? A Hamiltonian should be, kinetic energy plus potential energy, roughly speaking. Now, kinetic energy will be momentum squared term. So this we see here, right? These are momenta. They have two indices, so it's slightly more complicated than what we're used to, but this is what we expect for gravity. And this is a function that depends on coordinates. And it's exactly this function. So this tells you how to contract the momenta. So this is a natural momentum squared for gravity. This thing is called the de Witt metric, or rather the de Witt supermetric, which has nothing to do with supersymmetry and predates these developments by decades. And then we have kind of potential energy, and here we have the three-dimensional Ricci scalar appearing. So this appears in the Hamiltonian, but it appears in a special form. It's multiplied here into these other new functions. And the geometric meaning of that we'll discuss further tomorrow. So thank you, and see you then. Yes. Yes. It's all, the little thing is kappa. This is just the